Okay, hello all my calculus friends. It's Raj here, coming to you live, sort of, from my recording studio. Well, here in my living room, my high-tech setup. So I know I've worked a few examples, and some of you have watched that. Not many, but some. And anywho, today I'm going to do this whole lesson on how to find the volume of revolution. Whew. And we're going to look at the disk method today. So hopefully you have opened up the notes because you're going to need to look at those, and you can write if you can print those. That's awesome. Otherwise, you're going to need paper so that you can go through these examples with me and take notes of your very own and keep them. It's not ideal, but it's the way we got to do things these days. So I'll wait just a second here while everyone's gathering all their things, right? And while you're doing that, let me just mention that so far we've done area between two curves, where you take the top minus the bottom curve or the right minus the left curve and calculate your area. We also have looked at how to find the volume of cross sections. And volume means three-dimensional. And so what you do is you figure out a way to represent one rectangle when you're doing cross sections, and through integration you take the area of that shape and you get the volume. And for cross sections, depends, you could slice different types of shapes. So you could do an equilateral triangle, you could do a square, you could do a semicircle, and depending on what kind of shape you're slicing depends on what number you put in front of your integral as the coefficient. So for cross sections, you just figure out the way to represent one rectangle, the area of one rectangle, and then determine what number goes in front depending on the shape you're going to cut. Well, today, when we talk about disks, this is a little bit different also. So picture you are finding the volume, so it's three-dimensional, and what you're going to do is you're going to take some area and you're going to revolve it around an axis. And the first example we'll start with will revolve around the x-axis. And think about this, if you revolve it, it means it's coming out at you. It's three-dimensional, and it's a solid that's formed. And then we're going to slice into the solid. And a beautiful thing about these kind of, when you're revolving about a line or the x-axis or y-axis, all the shapes that you cut are going to be circles. So if we can figure out the way to represent the area of one of our circles through integration, we can add up and integrate and get the volume of a whole entire object. It's really cool stuff. So as you're looking at the notes, you can see the first picture for the disk method where they're talking about that representative rectangle. Well, that is your top minus your bottom if you're doing this with respect to x. Or that would be your right minus your left if you're doing it with respect to y. And I'm going to show you examples of each thing today. So if you want to find volume of a cylinder, right, because that would be the volume, you're going to take the area formula of a circle, which is pi r squared, and multiply it times the height. That gives you the volume. Well, for our purposes, we're going to think of volume as being pi, and I'm going to write big R because that's going to be our representative rectangle, our top minus our bottom, or our right minus our left, times a width. And we're going to translate that into an integral form in just a second. So as you can read through what these notes say, and I'm just trying to condense that real quickly. And you can look at the pictures and hopefully get a better feel for what this means when you do these revolutions, and how you're gonna slice into them and what it means. So if we have an axis of rotation that's a horizontal line, for example, the x-axis, then the discs we cut there are going to be when we integrate, it's going to be with respect to x, and we're going to be doing cutting vertical slices. When we do this with cutting horizontal slices and we revolve around something that is parallel to the y-axis, we're going to do that with dy. This will be all more understandable when we look at an example. Now let's talk about how this is going to work. If we can figure out a way to represent r, which is going to be top minus bottom, if we're doing this with respect to x, right, that'll be dx. Or if we're doing right minus left, that would be when we do this with respect to y, okay? We figure that out. All we have to do is go to our integral, and we're going to have bounds a to b. I like to put this pi out front because he's just coming along for a ride, right? Because he's a constant. Then we figure out either top minus bottom, right minus left. We put that in here. We have to square it because in the area formula that's squared. And then we put a dx or dy in there, depending on which direction we're doing. And this is the setup, no matter what you're doing. Now, a question always becomes like, how do I know if I'm doing a disk? And today it's not going to really matter because that's all we're going to look at today. But what you want to think about is the axis of rotation. And now we all are going to see that I'm going to call the axis of rotation, let's do this like this, is AOR. I just abbreviated AOR. That's what you're going to revolve around. And that tells you whether it's a disc or not. So today, everything is going to be a disc. Tomorrow, when we do washers, that'll change and be a little bit different. So now, if you look in the notes, it has a box of fun steps to find the volume of a solid using the disc method, which is what we're about to talk about. And so you always want to draw a picture. I know if you've done a lot of the area problems and the cross-section problems, pictures always help me. So you always want to draw a picture. You want to determine if the axis of revolution is completely connected. If it is part of the bounds of your shape, you're always going to be doing a disc. So that's a thing. Then if you want to, this is my arbitrary rectangle that it's talking about in those steps. This is what represents the slice I'm going to make, how I'm going to figure out what my R is. And then, of course, remember, this comes from Riemann sums when we learned about that, and we would add up the area of all these rectangles. Well, we do that through integration. We learned that we can do that through integration. So here we go. Let's try to do the first example here, which says find the volume by rotating the region bounded in the first quadrant. Okay, so that's good. I got to stay in the first quadrant. And it's going to be bounded by this equation, y equals 4 minus x squared. And the coordinate axes, which means the x and y axes. Okay, so that means I've tried to outline it here, that shape. And we're going to take this. So imagine taking this shape here and revolving around the x-axis. So this is my axis of rotation, and I'm going to revolve this shape around here. Okay. And if I slice through that, so I would have something three-dimensional, and if I slice through that, that would give me something circular. I know it's hard to picture on this two-dimensional page, but that would give me something circular. If I can figure out a way to represent this radius right here, remember if this goes all the way through and we go all the way around here, I'd have a piece of the curve down here too, right? And so this would be going all the way through. And if I sliced all the way through, I'd have a circle. So if I can figure out how to represent that one slice, I can then integrate and get a volume. Whew, so let's try this. We're revolving around the x-axis, all right? That's a horizontal revolution. So my axis of revolution is the x-axis. I want to do this with respect to x. I want my equations to be y equals, and my bounds are going to be along the x-axis. So for us, that's going to start here at 0, 0, and then we'd have to know where that crosses right there to figure out our bounds. All right, so since I just brought that up, let's figure that out. So this is a parabola, right? Is this one pretty simple to figure out that this is crossing at -2 and 2? We don't care about over here, right? Because we're just strictly in the first quadrant. So this is at +2. When I go to set this up, let's figure out our R now. We're going to slice vertically. That means I want to have my equation be y equals, which it already is. So, and I'm going to do the top minus the bottom. Well, what curve's on top? That would be the y minus x squared. What's on the bottom? That's y equals 0, right? Y equals 0. So if we did top minus bottom, it's going to look like this. We're going to have 4 minus x squared minus 0, right? Now, do I have to write that 0? I do not, but I'm just putting it in there to demonstrate that top minus bottom would be the curve y minus x squared, and the bottom is 0. So that's how we're going to represent, well, I squared it right here, so let's make that r squared. And we're going to go over here to our volume equation. Again, I like to just keep the pi outside, so don't forget you have to have pi. Who doesn't like good pi? But anyway, here we go. So we're going to go 0 to 2, right? Because our x, the shape is bounded from those x values. And we're going to do this. We're going to do 4 minus x squared. And now I'm not going to write the 0 because I don't really need it. I'm doing that with respect to x because I'm cutting vertical slices. And here's what I'd have to do. Now, in order to do this by hand, that might get a little ugly because guess what we'd have to do? Yep, you're right, a little algebra here, and we'd have to square that out, wouldn't we? And then we'd integrate each term, and then we'd do our bounds, top minus bottom, okay? So for our purposes here, in order for time, we're not going to do all that by hand. I have, in fact, punched this in the calculator, and you can check me, and I believe if I rounded to 3 decimal places, that represents the volume of this solid. And we just did our first volume problem. And it is a disc. And it is very exciting stuff. What do you guys think? You like that so much you want to try another one? Well, alrighty. Here we go. In your example 2, it says, find the volume of the solid formed by rotating the region bounded by the x-axis, y equals the square root of x, and the line x equals 4. And we're going to revolve this all about the x-axis. That's our axis of rotation again. That's horizontal. So we're going to take vertical slices because our axis of rotation again is right here. And it is a horizontal axis of rotation. So we're taking this shape right here. Let me get another color here. We're taking this shape right here. And I'm going to dot this to represent that it's revolving, right? If I take this and revolve this around that x-axis, and then I make a slice all the way through here, that slice is going to be circular. That's why we call this a disc. So if I have a disc slice going on here, I want to know how to represent the radius of one of these discs. Okay, so our R value is going to be, I hope you can see all this, y equals the square root of x, right? And x equals 4 is our line. In this case, this one starts at x equals 0 and goes to where x equals 4 right here. So when we set up our bounds to find our volume, we're doing pi because this is a disc, and we're going to go 0 to 4 because along our x-axis, those are the values that bound this curve. All right, and now we just need to figure out how we're going to set up this radius right here. And again, we're going to do top minus bottom because we're going to do this with respect to x. We want our equations to be y equals. So here we go. Top minus bottom would be the square root of x minus 0. Square root of x is on top. Y equals 0 is on the bottom. That's our R value. Put it in here, and we're going to have the square root of x minus 0 squared. Does that minus 0 matter? No, it does not. So this just turns into x, right? When we go to, if we squared this out, this one wouldn't be so bad to integrate, because we'd have to integrate from 0 to 4, just x. I'm fairly certain we can do that. Let's keep our pi outside. Remember, he's along for the ride. And then when we integrate that, we'd have x squared over 2, and we'd want to do that from 0 to 4, just making sure we remember all these lovely details. So that's going to be what? 16 divided by 2. Does everybody see that? 16 divided by 2 would be 8. So for 8 pi, that's the volume if we revolve this shape around the x-axis. Whew, look at us go. We did that whole thing by hand. What do you think? Not so bad. Again, because my axis of rotation was horizontal, that means my slices are going to be vertical. I'm going to use dx. And we're used to dx, so we like that. But just when we start thinking we got this all down, I know for most of us, when I posted a little survey from my calculus kids, they said, a lot of people said integrating with respect to y was a little bit confusing, which I get because we're not used to making equations x equals. We're used to using them in y equals form. So let's look at example 3 because this is going to change things up on us. Let's see if we can get this. So this says find the volume by rotating a region in the first quadrant. Okay, so just the first quadrant. And we want to be bounded by y equals the square root of 16 minus x squared. Did you know that's the semi part of a circle, actually a quarter circle, right? And our axis of rotation now, though, is this y-axis. You see the difference here? Now, I don't have a lot of room on my paper, but if I did this, right, we just imagine this kept going. And I'm going to take this stuff in the first quadrant and revolve it around there, like so. Huh, okay. So to find this, if we slice through this, this would have, our disc would go kind of like this when we revolve it and did a slice. So we want to represent the radius of one of those things, and we'll put it in the area formula of a circle and integrate it. We'll have volume. Well, here's the deal. My axis of rotation is the y-axis, okay? That's a vertical axis. I'm going to integrate with respect to y. I need my equations to be x equals. We're going to have to change this to make it x equals, okay? And then my bounds are going to go from 0. Now, in this example, it doesn't really matter, but 0 to 4, because I got to think of these y-axis bounds, right? Where is this shape bounded on the y-axis? Where if we were doing vertical slices this way, we'd go 0 to 4, but that would mean x-axis. Now, because you know, these are both 4, that's not going to make a whole lot of difference. But here's the problem. I have to make this x equals. So I need a little bit of algebra before I do this. So I'm going to square both sides. Won't I have y squared equals 16 minus x squared? And then I want to get x by itself. Look at this. What is that an equation of? You guessed it. That's a circle, isn't it? So if I want to get x by itself, I'm going to have 16 minus y squared. Oh, that looks kind of familiar. And then if I square root this to solve it, x equals, remember we would do plus or minus because we're taking a square root. Aha, look at that. Now, if I were to graph this, let me just go over here real quick. The graph's going to be the same as what I had over there. But if I were to graph this thing, if I did the positive side of this, it would be a semicircle like so. And this would be where x equaled 4, right? But this positive would be this side right here. And the negative square root would be this side over here, and I'd have a whole circle then. Where if I did it here when it's y equals, the positive side would be up here because that's where y is always positive, up above the x-axis, right? And then the negative square root would be down here. So over here, the positive square root of the positive square root of 16 minus y squared is this side. And isn't that on that side of the y-axis? Isn't that where x is always positive? Aha. Okay, well now we still want to slice this. We're going to make these horizontal slices. So now I have this, and I'm going to use the positive one, right? I need my equation to be x equals. Remember, that's what I set up here. And I'm going to integrate this with respect to y. Well, when we integrate with respect to y, we have to do right minus left to figure out our representative rectangle. So what curve is on the right? Well, that is the square root of 16 minus y squared, What's on the left? Well, that would be x equals 0. And so that would be how we represent our rectangle, our R value. Okay? Now, when we go to integrate this, remember we're finding volume, and it's of a disk, so we need our pi. The y bounds now go from 0 to 4 along the y-axis. Okay? And now I need my equation to be 16 minus y squared minus 0, and then remember this is going to be squared, and a dy. Do you see how when we were doing integration, and in my class I always stressed how important it was to have whether this was dy or dx, and this is exactly the reason why. Because it tells you what variable you're integrating with respect to. Now, if you notice, if you set this problem up and did this exact same thing, and this was x squared and this was dx, you're going to get the exact same answer. I can go to my calculator and plug this in and use x's right here instead of y's, and get the exact same answer because these are the exact same equation, right? All we did is change this variable right here, and that's not going to change the value of this. If you were to do this in your calculator, and of course you just plug in x's right here, you're going to get 134.041 if we do 3 decimal places. So yes, that would give you the same answer, but because they told me to revolve this around the y-axis, when I write this up to show my work, I got to have y's here, okay? And typically the equations aren't the exact same thing. That's just an example to show you how to integrate with respect to y. So hopefully that's not too bad. Okay? All right. We have 2 more examples we're going to do, and one is going to be a dx and one is going to be a dy. We got this. All right, so example 4 says, find the volume of the solid generated by revolving the region bounded by the graph x times y equals 6, the line y equals 4, and the line x equals 6. Our axis of rotation for this first one is going to be y equals 4. So now this is not the x or y axis, it is a line. Now, because this line is horizontal, which is like the x-axis, we're going to do this with respect to x. We want our equations to be y equals, and we're going to make vertical slices. So I drew a picture of this. Here's the line y equals 4. We're going to revolve it around this line right here. Okay? So if I were to take this shape that's right here and revolve it, right, my shape is going to look like that, and then my slices would be in here like that. Okay, so this is similar to when I revolve something around the x-axis. That axis of rotation is part of my shape, and therefore this is a disk. That doesn't make sense to you right now, but after tomorrow it should. And so now how are we going to set this up? Well, let's think about it. We need to figure out how to represent our rectangle, right? And so since we're slicing this vertically, we need to do top minus bottom. Now this is very important here, and this is why pictures help so much. The line y equals 4 is on top, and that curve is on the bottom. Wait a second, they wrote this equation x times y equals 6. Is that one an easy one to make y equals? I think I can make that y equals pretty easy. Won't that be 6 over x, like so? Okay. And so if I'm going to do top minus bottom, I need to do 4 minus 6 over x. And that's what I'm going to put into my volume. Volume equals... Oh, and now I just need some little bounds going on here. I need to figure out what this value is, and it's in between 1 and 2, and I believe this is x equals 6. So I need x bounds here because I'm doing this with respect to x. Do you remember how we find the bounds? Well, if I let y be 4, right? Let's go over here and do some side work. If I let y be 4, actually it probably would have been easier to do it there, but here we go. We'd have 4x equals 6 over 4, which is the same thing as 3 over 2, which is 1.5. All right, so when I go to set this up, I got to have pi in there. My bounds are going to go from 1.5 to x equals 6. So right here, that's where that place is. That's where that point of intersection is. And I'm really setting this equation equal to y equals 4 because I know that's the line y equals 4 and what it has to equal. And now I need to have my 4 minus 6 over x. That's going to be squared and a dx here. Aha! Very nice, very nice. And because I like you and I don't want to do all this, we're going to say that that answer is approximately 73.695. Okay. So again, let's recap. I'm doing the volume of the region bounded by this curve right here, the line y equals 4 and the line x equals 6. And because my axis of rotation is horizontal, I'm going to have a vertical slice here. That would make it dx, y equals equations. I need x bounds because this is dx. So the last example here we're going to do, we look at the same region as above, everything is the same except for they're changing this axis of rotation on us. And instead of it being the line y equals 4, it's going to be the line x equals 6. So we're going to revolve this around this way. Okay, and then we slice through here. And so we'd have discs going through here, like so. All right, so that means I need dy. I need my equation to be x equals, well, that's pretty simple, right? It's going to look like that. And I need bounds along the y-axis. So I need to know what this value is here, and I believe that's a 1. I think this would be easy to figure out if we plugged in x equals 6 right here. I think we're going to get y equals 1 out. That's pretty easy to see. Okay, now when I do this way, dy, I've got to set up for my volume. Oh, sorry, let's not do that yet. Let's find our r, right? We're going to figure out how to represent our slice. And when we do dy, we got to do what's on the right, what's on the left. So I'm going to my axis of rotation, and if I draw to that outside curve, the thing that's on the right is x equals 6, right, that line, and then minus this 6 minus y. So that's how we represent one slice. We're going to put it in our volume formula. So here we go. The volume is going to be, smack a pi in there, right? What did we say these bounds go from 1 to 4 along this axis, right? The y-axis, 1 to 4. And then we're going to put 6 minus 6 over y squared dy. And then if you put that in your calculator, which I know you all are checking me to make sure, you're going to get that value right there. So hopefully this fun with discs, volumes of discs, is understandable. You guys let me know what questions you have so we can maybe work that out, and then there'll be practice for you to do. Love you, miss you, bye.